So here we are, day 8. This is the lecture. This is more or less a summary of the lecture from Friday I guess that would be 8th? Yeah, Friday the 8th of February. There's a couple things that we want to talk about, restriction mapping, and we also wanted to talk about the polymerase chain reaction, or PCR. And we're going to go ahead and begin doing that shortly. So the first thing that I want to talk to you about is PCR, the polymerase chain reaction. Now, what the polymerase chain reaction did is it totally revolutionized how biological or life science research is conducted. At its heart, here's what the polymerase chain reaction consists of. Oopsies. So I'm going to delete that. The polymerase chain reaction starts with a piece of double-stranded DNA. Here's our double-stranded piece of DNA. And what we are going to do is we're going to heat this to approximately 98 degrees Celsius. Whenever you're heating that, what are you going to be doing? You're going to be disrupting hydrogen bonds. The hydrogen bonds that hold this double-stranded piece of DNA together. The result of this is that there's one strand and another strand. This is ds-DNA, and this is 1ss DNA. One single-stranded piece of DNA, and here's our other strand, or a single-stranded piece of DNA. We have this on the 5' to 3' direction, and this is the 5' to 3' direction down here. Now, whenever we have these two pieces of DNA separated, what we can do is then cool our sample down and add what are known as DNA primers. These DNA primers will bind to are single strands of DNA. Again, they have 5' to 3' ends, 5' to 3' ends, and we have new double-stranded chunks of DNA that are separate, that are brought together. This takes place whenever you lower the sample down to about 55 degrees Celsius. Now, after that is where the action actually takes place, and at that point in time, we have DNA polymerase that is going to see these double-stranded pieces of DNA. And I'm going to draw the double-strand or the DNA pol as that. So the DNA polymerase is going to bind onto that, and it's going to slowly but surely proceed in this direction, and this one in the opposite direction. And we're going to begin making new pieces of DNA. So new double strands. And whenever we do that, well, now we've taken one piece of double-stranded DNA to make two identical pieces of double-stranded DNA. What's important to know about this is that this DNA polymerase is not actually going to do anything until you're at about 72 degrees Celsius, or if it does something, it's going to be doing it at a much lower rate. Whenever it's at 72 degrees Celsius, that's a optimal temperature for that DNA polymerase. Now, so these are basically the three major steps. First, we separate or we denature our double-stranded DNA. Then what we are going to do is we're going to anneal, and then finally we're going to polymerize. We are going to make our new pieces of DNA we're going to synthesize new pieces of DNA. So denaturation or melting is what the first step is called. The second step is going to be annealing or hybridization. The third step is polymerization. These take place at finite temperatures, approximately 98 degrees, approximately 55 degrees, and 72 degrees Celsius. So all of these steps are going to take place, but what do we have to have present in order for this to actually go? Step number 2, one of the things that we have to have a collection of every single nucleotide. And since we're making a piece of DNA, we have to have deoxynucleotide triphosphates, DNTPs. Now, in addition to that, we're going to have a cation like magnesium, because that magnesium is going to stabilize the alpha, beta, and gamma phosphates on that nucleotide triphosphate. So we're going to generate these new pieces of DNA with the help of nucleotide triphosphates. So once this is all said and done, you're going to go from, a very small amount of DNA to tons and tons of new DNA. And so you're going to do these 3 steps. So do 3 steps over and over again. And you're going to do it approximately 30, anywhere from 30 to 40 times, so that you can actually blow up that amount of DNA that's present. That's kind of the take-home message from PCR. What I want you to do now is get ready to talk about restriction mapping and restriction digestion. So we'll proceed with that. Okay, so now what I want to do is I want to talk about restriction mapping. Restriction mapping is a process where you are given a piece of DNA, and you are tasked with finding out where does it cut, or where is it cut. And to answer this question, what you need to do is you need to basically subject it to digestion with a number of different pieces of a number of different restriction enzymes. So as an example, I'm going to work through a problem. This is different from the one that we did in lecture, but essentially drives up the same principle. So this question says that students performed a set of restriction digests on newly isolated plasmid, PBLA230, PBLA230. Now, whenever you see this lowercase p there, or if you hear the term plasmid, you should think about this as a circular piece of DNA. So what that means is if a restriction enzyme cuts at one time, well, that basically takes that circle and opens it up. So now it's a linear piece of DNA. It has a pair of ends, whereas a circle has no ends to it. Okay, so this piece of DNA, when it's digested with the following restriction enzymes, has the following products. So whenever you cut it with HPA1, you will get a 26 kb piece of DNA. Whenever you cut it with HIND3, another restriction enzyme, you will get a 13, a 6, a 4, and a 3 kb piece of DNA. And finally, when you do a digestion of HPA1 plus HIND3, you will get the following digestion pattern. You will get a 7, a 6, a 4, and a 3. So what this ultimately boils down to is, what does your DNA gel look like? Well, let's go ahead and put together a DNA gel. So A, B, C. I'm going to pause. Okay, so we have PBLA 230. It gets cut. It has the following results, and I'm just going to put A, B, and C. I'm looking at the relative migrations of all these different bands. I'm not going to put a molecular weight ladder, but a molecular ladder would be in this column right here, and it's just going to show you different standards. So for column A, I'm going to put this line right here. That indicates 26 kilobase pairs. Okay, so that band is 26 kilobase pairs. It does not migrate very far because it is so large. Now B shows us that we have a 13 kb band, a 6, a 4, and a 3. Okay, column C gives us the double digestion, where we have a 7, a 6, a 4, and a 3. Okay, so we've got a 7 right here, a 6, a 4, and a 3. Now what you can do with this is you can go ahead and add up all of the different molecular weight sizes. We've got 26. In B we have 13 plus 6 plus 4 plus 3. That adds up to 26. So I'm going to write 26, indicating that I've reached that. Now C gives us 7, 6, 4, and 3. So that would ultimately add up to 7 plus 6 is 13, plus 4 is 17, plus 3. That only gets us to 20. And we need to get to 26. So what that means is that this band right here, our 6 kb band, well, that's a neat one and a unique one because of the fact that, well, likely what's happening there is we have two different fragments of the exact same length. So I'm going to write 2x. So if we had another one of those, or since we have another one of those, an identical length band, that gets us to 26 kb. Now, this right here is kind of half the battle, being able to draw a DNA gel. Now, after that, though, what we need to do is we need to be able to take a circular piece of DNA and make an approximation as to where these different bands are. So the way that I like to do this, or I'm sorry, not bands, but instead where these different enzymes cut. The way that I like to do it is I like to draw out 3, oopsies, I'm going to erase that. I like to draw out 3 bands for my 3 different digestions. 1, 2, 3. Okay, and then those are kind of my practice space. So I'm going to say that this one is A, this one is B, and this one is C. I've drawn four of them, and I might just make C and this one right here kind of interchangeable. Little rough drafts. Okay, so for A, what we know is that we have a 26 kb piece of DNA. HPA1 cuts 1 time, straight down the middle. That one band right there is going to, or that one HPA1 cut site is going to give us the product that we're looking for. Now, B gives us 13, 6, 4, and 3. Okay, so how do we actually split that up? How do we split up a 26 kb fragment into 13, 6, 4, and 3? And really all that we need to do is basically draw some lines. We'll say that this is 13, this is 6, this is 4, and this is 3. Based on the information that we have, there's really no other way that we could organize this and be, I guess, more correct. So what I've drawn for A and B, in both cases, it's right just as much as it's wrong. Now the real testing ground comes whenever we look at sample C, our double digestion. What do we know? What I'm going to start out with, and I'm going to bounce around with a couple different colors. I'm going to go ahead and draw that right there for HPA1. Because we know that HPA1 cuts and gives us a 26 kb fragment. Now after that, I'm confronted immediately with kind of a challenge, and that is the 7 and the 6. And I know that because of my DNA gel, I have 2 samples that are 6 kb. Now, the question is, where does this HPA1 cut site fall on this banding pattern? And the answer to that is, well, it's kind of simple. We go from a 13 kb fragment to a 7 and a 6 and a 4 and a 3. The 4 is common. The 3 is common. The 6 is also common. But one thing that we do know is that 13, that is a good way to come up with a 7 and a 6. So where does the HPA1 cut site fall here? Probably right there, which would negate this 13 and give us a 6 and a 7. So an accurate way to draw this map is to go with, just a second, to place all your Hind 3 sites. Hind, then boom, so that gives us 3 fragments, Hind, Hind. This is 13, this is 6, 4, 3. I draw that right there for my HPA1. Now, based on the information that we have, this is correct. We have a 6 and a 7. Could this alternatively be 7 and 6? Absolutely, but based on the data that we have, considering that we only cut with 2 restriction enzymes, this answer right here is completely acceptable. So the goal with a restriction mapping problem is to find out where the different enzymes cut a piece of DNA. Whether that piece of DNA is linear or circular, it just depends on the problem at hand. Anyway, I hope this was helpful. Thank you very much for watching, and have a good afternoon. And good luck prepping for the exam.